I had to turn it on twice. Yeah, so we help the teams to collaborate on the designs, and you actually don't need the design software like Photoshop to open designs in Avocode. We achieve this by building a technology that can convert all these supported formats to our own format. We call it Octopus. And we have also built a 2D rendering engine that can render these designs pretty precisely. So you can open the design and it appears very similar or usually the same as in the original design software. This requires a lot of various workload to be deployed on our servers. Here is a simplified diagram of what we have deployed. There is a client Avocode app, which is a React UI web or a native Electron application. It's communicating with a Django application, which is a standard combo of Django, Celery, and PostgreSQL database. The Django application itself is communicating with a whole ecosystem of different design processing workers using RabbitMQ. These processing workers usually just get their input files from a Google Cloud Storage bucket, do some work on it, and upload the output back. Apart from these two, we also run a lot of infrastructure in our clusters, like our own GitLab on-prem instance or telemetry services like Elasticsearch for logs and Prometheus for monitoring all of our services. To give you some idea of the scale we operate, it's around 64 unique services deployed in our cluster, each of them usually in 2 or more environments. The cluster is large, around 400 CPU cores and terabyte of memory, but this changes a lot around day and night. We have 17 developers actively pushing new images, around 60 deployments per day. So the cluster is not super massive, but it was enough scale to run into a few issues. Now, this concludes my introduction, and in this presentation I'm going to talk about 6 different lessons we learned while operating the Kubernetes cluster for the last 2 years. First one is pretty general, and it doesn't apply just to Kubernetes. Lesson 1 is don't over-engineer, be boring. What this means. So today it's really easy to follow shiny new technologies. They come up every week. There's something new. Everyone is talking about it. And it's easy to follow the temptation and start using these new tech very fast. But you should think about all new technology as a liability, because software fails and you need to know how the whole stack works, what are the failure modes, and what can fail. So some startups say, I need Kubernetes for my web page and 2 microservices, but this is often overkill, as you can see on the image, and there are definitely more effective solutions for smaller projects for production deployment. For us, it was very useful to start using Kubernetes. It offers a lot of powerful abstractions. It streamlined our management, give us more visibility into the in our infrastructure, and helped us dealing with autoscaling. It's nice that it can work on any cloud platform. It's platform agnostic. It's actually helped us when we needed to migrate from Amazon to Google Cloud Platform, and it was much easier thanks to being already on Kubernetes. Even after you have adopted Kubernetes, it's just a platform and you need to do a lot of decisions afterwards. There is a lot of new shiny things coming to being released, and everyone is talking about it. One of them, like example, is service mesh, like Istio or others. Everyone is talking about it. It does solve a lot of problems, but it completely changes how the application communicates with each other, so, and adds a small overhead. So we haven't adopted it yet, but it's still a good idea to look at such new technologies, because you can even experiment with them. but always think about, try to be conservative in your infrastructure. Lesson number 2, don't manage everything yourself. So cloud providers usually give you a lot of options on how to run a lot of different managed services like databases, Kubernetes itself, or other states service. In general, managed services lock you in to the provider and can add a little bit cost, but on the other hand, it insulates your team from having to know every failure mode. They don't need how to operate the service, and that can be very useful. Especially in smaller teams like we are, you should focus on your core competency, and that's often not managing database, for example, which is a great example because they need to be available all the time. You need to set up replicas and failover, sharding in some cases. You need to be able to back up it periodically and be able to recover easily. And it has a lot of failure modes in general. So you need to ask yourself, does managing the database provide enough value for me? In some cases, you can be a, I don't know, fintech company which needs some Postgres extensions or some complicated real-time database transaction. It could be your core competency, and it could make sense to manage your own database. For us, it was not really the core, so far we are using a managed database solution. Lesson number 3, expect failure, embrace failure. So in our case, we are using spot instances in Amazon, which is a special type of server, which doesn't have any uptime guarantees. This means it can be killed at any point. On the other hand, it's just a fifth of the cost of the normal server. So if you can handle this termination well, you can actually decrease your infrastructure cost by 80%, which is great. In Amazon, we observed that a lot of these spot instances actually stayed online for days, even weeks. So we didn't even need to handle some of these terminations that well. After we migrated to Google Cloud Platform, there is an alternative that works a little bit differently. It is called preemptible instance. And the difference is that preemptible instances in Google Cloud are always deleted after 24 hours. So they will always delete after 24 hours, sometimes even sooner if there is not enough, if there is a zone exhaustion, for example. So we thought we were handling failure well before, but as soon as we moved from Amazon to Google Cloud Platform, we identified a ton of new issues that could happen. But on the other hand, thanks to these like preemptible nodes failing constantly in a planned way, we learned to expect it and improved our stack to actually handle such failure better. So now when servers go down for other reasons, like a real networking issue in Google or some other issue, it often doesn't have as big impact on our availability, or it doesn't have any impact in some cases. So it's kind of like a chaos testing tool in a way. And it's a good idea to monitor your components and test your whole stack by, for example, killing one component and look at your own or whole architecture and see if the failure is isolated and or the whole architecture can work around it. So lesson number 4, when all fails, define a clear response path. What this means. Even after you make your services or your whole stack highly available, at some point downtime affecting customers will happen. It's important to be prepared for such situation. In our case, we use a standard on-call system, which means every week there is one on-call person who's responsible to resolve incidents. We have automated alerts on all these major components that can fail, like processing designs, for example. And when this alert is triggered, it can call you in the middle of the night and you need to resolve such issue. Important thing about this is to have good documentation. Every such alert has a runbook, which is a specific documentation for this type of alert, which gives the on-call person clear guidelines on how to investigate such issue and guide him to resolution. Second important part is after the incident is resolved, you had some downtime, but it's already up. After you return to office, for example, it's important to do post-mortem. This means you need to investigate, you should document what happened actually, have a timeline of actions that happened that caused the downtime, for example, and try to find out as much issues and try to identify as much issues and try to find the root cause of the incident. Finding root cause is like a topic of its own, and I think the most important in this is be blameless. This means you shouldn't focus on which developer did what mistake. You should focus on why and how the mistake happened. So finally, you need to define some action steps, and these action steps should prevent your company from making the same mistake in the future. It doesn't need to be just like changing your, I don't know, application or your infrastructure. It can also be some new team process you set up. For example, never deploy on Friday night just before everyone leaves the office and such. So the next lesson is lesson 5. For us, it was put things in queues. This seems pretty obvious for like design processing, and it's part of our strategy for handling failure and bursty workload. For us, queues handle both of these pretty well. If a task gets interrupted, the message is returned back to queue and retried by a different worker. We auto-scale based on the queue size, so we can be very dynamic, and coupled with some rate limits, it's very powerful and can handle these bursty workloads. A good infrastructure team is usually building a good platform for your developers. What we did is we built a common library that can handle all these infrastructure concerns you have, like getting tasks from the queue, getting the input files from object storage like Google Cloud Storage, or uploading the output files back, and making the retry policy sane. And so what we did this tool, and developers can only focus on the actual business logic of the worker. They can leverage this tool to focus just on that. One pattern we use a lot across, I think, all of our workers that process data. Thanks to the distribution of the task in our case, usually we need just minimal resources for 95 or even 98% of all the tasks. For example, people upload PSD files, designs. Usually they are pretty easy to parse and process, but from time to time there is a crazy designer that puts a world map of the whole world with 50,000 of vectors, and it's much harder to resource a design to process a design like that. So what we have set up, we look at our metrics and we try to find out what resources do we need to process like 95% of our tasks, like 95% of designs uploaded. And we set up first a normal worker, which is with much less resources, like half core and half gig of memory in this case. And this processing worker can actually process most of these normal designs, but in some cases, for these edge cases, all failed tasks go to a fallback queue with another worker, which is the same Docker image, the same application, just with a little bit different resources configuration. This works very better and saved us a lot of money because the normal worker doesn't need as much resources as you would normally need, and you can also run a lot less of these fallback workers. Actually, most of the time we run 0 of these fallback workers and just start them if there is demand. So the last lesson number 6. Sometimes you have to help the scheduler out. This is about the Kubernetes pod and node scheduling. We run Kubernetes with these, with autoscaling of these containers named pod in Kubernetes, and at the application level, and these pods need to fit into some servers. These are called nodes in Kubernetes. So our workload can be very bursty, that we need to, for example, run a lot of new workers at some point, let them work for a few minutes and then shut them all down. And we noticed with this workflow that the schedulers sometimes struggles, and we saw a lot of stranded resources. What this means in this case is, if you look at node 2, there are two containers. They are the green and the red one. They are using 100% of the CPU of this node, but only half of its memory. because 100% of CPU is used, you can't really schedule another pod here, and the remaining memory is lost and cannot be used or stranded, as we say. In our case, we noticed that our containers had only a few different ratios of resources. That means that a lot of them needed like 2 gigs of memory for 1 core of CPU, or one core for 1 gig, and so on. So what we did is we created several node types, each for one of these ratios, and we can tell the scheduler a rule that for some of these pods, especially these bursty workers that needs to be scheduled a lot of time and scaled down later, these pods have to only land on the nodes with the same resource ratio specified. So this actually limited the stranded memory issue a lot for us and saved us about 20% of our monthly costs for servers. So that concludes my presentation. Thank you. If you have any questions, feel free to ask. I will be giving a sticker for each of your questions. Yeah. No. Mm-hmm. Mm-hmm. Yeah. Basically, what we did is very similar. Like sorry. The question of if we heard or saw the new like serverless platforms. Yeah, Google Cloud Functions. Yeah. We actually experiment with it and will maybe start using some of these. But so far, actually, like feature-wise, what we built had more features, or it's more. A lot of the features we built are not present in these solutions. Like, I don't know, even Google Functions couldn't scale to 0. I think they added that feature now, but we are looking into it and probably we'll leverage it in the future, maybe in some cases. Yeah. I'm just like, I'm a CTO, so I was developer, DevOps, like all of this stuff. And I've heard about this, yeah. So which one of, or do you want? Spaceship should be here. Yeah. Yeah, thanks. Or should I add something, or we can talk later. Last question, if anyone. Okay. Like it's like for Google Cloud. Yeah. What's the saving of Google Cloud preemptible instances compared to Amazon Spot? Yeah, it's pretty similar. I think for Google, it's you save 80%. For Amazon, it's some kind of auction, so the price differs all the time. I think it was also something like 80% saved. Mm-hmm. Yeah. So that was the last question. Thank you.